You all are welcome for today's lecture. Yesterday we discussed about the orthogonal coordinate system. Under the orthogonal coordinate system, we have discussed the two type of orthogonal coordinate system called the Cartesian coordinates and cylindrical coordinates system. Today I will discuss the another orthogonal coordinate system called spherical coordinate system. We call this a spherical coordinate system. With the support of these spherical coordinates, we can locate any point on this space. I'll explain you how to do that one. I'll explain it. Just assume these are x, y, z axes. This is very familiar thing for you. So here we can locate any point by using spherical coordinate system. I will explain how to do that one. In this case, I will refer distance and to angle to locate any point on the 3D space. For example, I refer spherical shape to locate this any point. As example, just look. So I will refer this type of sphere to locate any point. For example, just look here. So if you want to locate a point here or here, just assume point P, I will refer to locate the positions of this P. I will do this type of picture. So this is my interested point. To express this point, I will refer R, theta, and phi values, right? So I will explain how to define this theta and other stuff. Theta measure with respect to this x-axis, right? So it's phi. This phi angle. Theta measure with respect to z-axis. As well as I measure another distance r from origin. This one represents the r. This distance represents the r. As you know, if you know this r and theta, just assume this differential angle, this small angle as d theta, and this angle assume as d phi. Then you can write down this length with the support of r and d theta. This distance you can write down r into d theta. As you know, you can write down s equal r theta with the support of the radian values of this theta. And similarly, what you can do, you can write down the distance of this one also. How do you do that one? You can write down that one r sine theta into d phi. R sine theta into d phi. You can write down that one. R sine theta into d phi. This length you can write down something like that. Here we define the unit vectors also. We define 3 unit vectors. One is UR. The direction is along this axis. Direction for UR is here. This is a unit vector. As well as we are defining another unit vector along this way. This is U phi. The direction is always changing. When your point is changing, the direction of this U phi always vary. As well as we define another unit vector tangent to this point. It is along with this way. This is U theta unit vector. So here we define this type of 3 vector, UR, U theta and U phi. With the support of this R, theta and phi, I can locate any point on the space. This mechanism we call the spherical coordinate system. This mechanism we call the spherical coordinate system. In this coordinate system, you can see here with the support of this 2 angle and the length, you can express the position exactly. Therefore, if you want to write down a vector A with respect to the spherical coordinates, you can write down that one in this form. The spherical coordinate system is most appropriate when dealing with the problem having degree of spherical symmetry. There are some applications. If you want to find the electric field intensity, flux density, something like that, under such computations, you have to deal with the spherical stuff. Under such conditions, better to use the spherical coordinate system to solve such question easily. This UR, U theta and U phi are unit vector which are orthogonal to each other. You can see here U phi defined along this way, and this U theta, U phi is along this way, and UR along this R. These all unit vectors are perpendicular to each other. These are orthogonal. These are orthogonal. These are orthogonal. So write down this figure, then you can get some idea. As you know, this R is a length. R is a length. Therefore, the conversion factor for this parameter H1 become 1. The next parameter is theta. You can see here this differential length. You have write down R into d theta. This R is the conversion factor for the theta. And similarly, R sine theta is the conversion factor for the phi. Therefore, I'll write down this H2 equal R, H3 equal R sine theta. These are we call the conversion factors. If you represent one axis as a length, then the conversion factor is equal 1. Here, your theta and phi is not the length. Those are representing the angle. In this case, These are the conversion factors for the theta and phi. This is the conversion factor for the theta, and this is the conversion factor for the phi. Therefore, I refer these values for the conversion factors. This is story behind that. Therefore, with the support of this spherical coordinates, as you know, you can see here the arc length, differential arc length of dl, you can write down by using this h1 d n1 u n1 concept. We have discussed these things. Based on this concept, you can write down the arc length with the support of this ur, u theta, and u phi. These are conversion factors. This is the conversion factor. This is the conversion factor here. And similarly, you can write down the surface area. You can define here surface area. Something like this. So these cubic having 6 surfaces. These surfaces you can write down. This DSR mean this surface. Right? So if you consider, if I draw this a little bit, it's too small. Just assume this is the differential volume what we selected there. What we selected there. This surface represents that DSR. The unit vector is perpendicular to this surface area. It is along with the R, UR. And similarly, this surface, you can find this is dr, this is dr, right? And this length, you know, r d theta. Therefore, you can write down that surface area of d s phi. This one should be phi r d theta into dr. This one dr. This is the surface area. This length equal to r d theta. This length dr. Therefore, this one represent this surface. This is the surface, right? As well as the theta surface mean this one. This is the surface. This is the surface area. This one represent this surface area. This length I have written r sine theta d phi, and you know this length. Therefore, you can easily write down this surface area. R sine theta, and this length also you know. Therefore, you can easily write down this surface area. So this is the procedures. Please draw the diagram clearly and show this surface area where it is. This is the dr. This is the surface area representing dr. Sorry, SR. This is SR surface. Try to familiar with this concept. Please put your registration number and the name to the chat box as attendance. Just draw a picture clearly and mark these lens surfaces. The given picture is not clear, therefore write down this one. Here we select the sphere with having radius of simple r. With the support of this sphere, we always try to place the point on the surface of the sphere. Our point P is located on the surface of the selected sphere with having radius of simple r. The radius of this sphere is simple r. The selected point P is always located on the surface. Keep in mind that this point P always located on the surface of the sphere. This is 3D sphere. Here we refer the sphere, this type of sphere. With the support of this sphere, you can increase the radius. With the support of this sphere, you can locate any point. Only thing is you have to change the radius. But once you increase the radius, the size of the sphere will be varied. That's the point here.
Ayuhan.
So if you go through this note, similarly, you can write down the differential volume. This is the equation for that volume. So dV represent this volume. dV represent this volume. dV. With the support of this or length correspond to this cube, you can write down the equation for the volume. You know this height is dr. This one r d theta. There's a relationship in between these AR and Cartesian coordinates. You can refer this expansion, as well as you can find the value for this r, theta, and phi with the support of this XYZ axes. This conversion you can do. You can find or you can write down a value for r. For example, if you want to find this r means this distance R means this one. So if you want to find this distance, this is the R. This is the R. That R you can measure by using this equation. As well as this theta you can write down by using this xy coordinates, because this P having xyz coordinates. If you locate this one to here, something like this. So you have x coordinates here, you have x coordinate here, you have y coordinates here, here you have x values, here you can find the y value, as well as you have z values also. You have z values. As I mentioned previously, you can find the relationship in between R and theta by using these equations. You can see the behavior of this or the similarity or relationship in between Cartesian coordinate and spherical coordinate by using this equation. So there are some relationship. So now I'll go to next topic. As you know, there are two types of product we are considering related to the vectors. We call it dot product and the cross product. Definitely, you know these things under advanced level. We have learned this dot product and cross product, but we will see for the 3D space how those are behaved. So scalar product, or what we call the dot product, is defined something like this. Just assume you have vectors of A and another vector B. This is A, this is B. The angle between this A and B is theta. The cross product is defined, so this dot product, or we call the scalar product, we define something like this. This is a definition. A represents a vector, B representing a vector. The results will become amplitude of A into amplitude of B into cross product, cross value. So cos theta. The theta represents the angle in between these two vectors. This simple represents the amplitude, okay, amplitude values. This is the procedure how to find the amplitude value. By using these definitions, you can find the amplitude of this A or B. As well as if you know the results, you can write down the relationship for the theta also. Here, you can see we are taking dot product. At that time, you have a cos theta term. If theta equals 0, then this cos theta become 1. Therefore, this un into un mean unit vectors along the n1 axis. If you took the dot product in between these two unit vector, your results become 1. If you use the dot product of this un2 into un2 or un3 into un3, you are getting 0. As well as these are orthogonal to each other. Therefore, the angle in between this un and un2, theta equal 90. Therefore, cos theta become cos 90 equals 0. Therefore, if you took the dot product in between these orthogonal unit vectors, your results become 0. Your results become 0. Those are some features. Therefore, if you took the dot product in between A and B vectors, your results become something like that. A is something like this. A is AX UX plus AY UY plus AZ UZ, something like that. B is BX UX plus BY UY plus BZ UZ, something like that. If you took the dot product in between these two terms, you are getting these values, product of these things. If you took the dot product in between the UX and UY, the result becomes 0. And similarly, you can apply this dot product for the cylindrical coordinates. If it is cylindrical coordinate, your results become something like this. You can apply this concept for the spherical coordinates, then your results become something like that. Here, UR dot U theta or U phi becomes 0. UR dot U theta equals 0. Something like that. Therefore, your results become something like this for the spherical, Cartesian, and cylindrical coordinates. Just to aware, okay, just read the document and familiar with the concepts. And similarly, cross product we define, just assume you have a vector A and vector B. Cross product we define, your results become a vector. The direction is perpendicular to this plane. With the support of this vector A and B, you can define a plane. This UN is perpendicular to this plane. UN is along with this way. UN is along with this way. That is perpendicular to the surface which is in between A and B. This is the plane. This UN is perpendicular to the given plane. So here the results become A cross bar equal amplitude of A into amplitude of B into the angle is in between this A and B represent theta, sine theta into UN is a unit vector along perpendicular to this shown plane. This is the direction. So here you can find A cross B, and similarly you can define B cross A. The only difference is sine theta into you are getting minus UN directions. If you took the B cross A, the direction for the unit vector is along this way. Unit vector is along this way. This is minus UN. The direction will change. Once you take the cross product, when you take the cross product in between this unit vector, you have a sine theta term. When theta equals 0, sine theta becomes 0. Therefore, when you take the cross product in between these same unit vectors, your result becomes 0. When theta equal 90, then sine 90 equal to 1. Therefore, when you take the cross product in between these orthogonal unit vectors, you are getting again a vector which is orthogonal to each other. When you take the cross product between UN1 into UN2, you are getting UN3. When you take the N2 into N3, you are getting 1. When you take the cross product between UN3 into UN1, you are getting UN2, something like that. Because these unit vectors are orthogonal to each other. UN1, UN2, UN3 are follow the right-hand rule. These axes are obey with the right-hand rules. Therefore, when you take the cross product, you are getting the another unit vector perpendicular to each other with obeying with the right-hand rule. These axes are with the follow the right-hand rule. If you want to take the cross product in between two vectors, this is the easiest way to expand the relationship. With the support of this matrix, you can expand this general form for the cross product, whether it is spherical or whether it's cylindrical or whether it's Cartesian, not a matter. You can deploy this mechanism. For example, this one represents the Cartesian coordinate. This one represents the cylindrical coordinate system. This one represents the spherical coordinates. The coordinate system is not a matter if those are orthogonal coordinate system, then you can use this matrix to expand to find the A cross B. Better to memorize this matrix, and you can expand based on whatever any coordinate system. This is a general expression. With the support of this general expression, you can write down. I think that is enough for today. Just read this document, and again we have a lecture maybe tomorrow, then I'll conclude. I'll continue. So I have enough time because we are not writing a lecture note, therefore I'm serving some time. So read this document and then try to familiar with this thing. Better to read this document 2-3 times. But once I complete this document, again, I will not provide this type of document. Okay, I will use the board to write all the things. To make a solid start, what I did, I gave the lecture note for you to get the good start for the module. And now once I complete this chapter, then I will not give this type of well-prepared lecture note. I write down on the screen and you had note down everything. Okay. So just go through this document. Tomorrow I will discuss these things. So I will stop today's lecture. Have a nice day for you.